In this video, you'll learn all about binary. More specifically, here's a list of every topic we'll talk about. Chapters are available if you want to skip to a particular section, and that's it. Let's go. In everyday life, we use the decimal system, also called base 10. Binary, on the other hand, is called base 2. This base tells us how many numerals the system uses. Decimal has 10 numerals, 0 through 9, and binary has 2 numerals, 0 and 1. Now, as you know, a decimal number has places, like the ones place, tens place, and so on. These places are powers of 10 because we have 10 numerals. Therefore, in binary, we should have a ones place, twos place, fours place, eights place, 16s place, and so on, because we're dealing with powers of 2. And believe it or not, that's all there is to it. To convert a binary number into decimal, we take each place and multiply it by its numeral. In other words, we take all places that have a numeral of 1. Then we add them all up, and that's our binary number in decimal. To convert from decimal to binary, we'll go over each possible digit starting from the first place that is smaller than our number. 123 is larger than 64, so we set this place to 1 and remove 64 from our number. 59 is larger than 32, so we set another 1 and subtract 32. 27 is also larger than 16, so that's another 1. 11 is larger than 8. And now we have 3 left. 3 is smaller than our fourth place, so we skip this one and leave it 0. Then 3 is larger than 2, and the last one is going to be a perfect 1. There are 2 other methods of converting between decimal and binary that I like even more. Take any decimal number, I chose 172, then divide it by 2 with the remainder. Take the result and divide it by 2 with the remainder. Keep doing this until you reach 0. As you might have guessed, the remainders form 172 in binary. The same works in reverse. Starting at 0, multiply by 2, then add the first binary digit. Then we take the result, multiply it by 2, and add the second binary digit. Repeat this for all digits and we get back to our original number in decimal. Just as in decimal, we can perform arithmetic on our binary numbers. To add 2 binary numbers, write them down and add each column one by one. When a column adds up to 2, like here, which is 1, 0 in binary, we carry a 1 and write down a 0. When a column adds up to 3, which is 1, 1, we carry a 1 and write a 1. Now let's subtract 2 numbers by subtracting each column. When we can't subtract because the result would be less than 0, we borrow. Here we borrowed a 1 from the next place into 2 1s in the current place. These are essentially being added to our top number now. That means we have 1 plus 1 minus 1, which is 1. Then we continue and keep borrowing if necessary. Multiplication is even easier. We multiply our first number with each digit of the second number. As we only have zeros and ones, this just creates identical copies that are offset accordingly. Adding these together then gives us the final result. And finally, division. First, we rearrange the dividend and divisor. Then we check if 100 fits into our first 1. It doesn't, so we write down a 0 and continue. 100 still doesn't fit into 1, 1, so that's another 0. 100 does fit into 110, so we write down a 1, subtract 100 from 110, and get the remainder. Now does 100 fit into 100? Yep, so that's another 1, and we have no remainder left. Pretty simple stuff. There is, however, something to look out for: overflows and underflows. In computer science, we often limit ourselves to a specific number of binary digits. Let's say we are limited to 8 binary digits. What happens when we add two numbers together and the result takes up more than 8 digits? This is what's called an overflow. As you can see here, our result ends up using 9 digits, even though we are limited to 8. The solution is quite simple. We just cut off the most significant digit. When we do this, our number essentially wraps back around 0. The same thing can happen when a number goes below its minimum value, except that's called an underflow. We also have some special operations in binary called Bitwise Operations. By the way, bit just means binary digit, but you probably knew that already. Our first operation is called the AND operation. We look at each column, and if both the top and the bottom digit are a 1, then the resulting digit will also be a 1. When programming, the AND operation can be quite useful to check the state of individual bits. Next is the OR operation. Here, each column results in a 1 if the top or the bottom digit is a 1. This one's useful to set specific bits in an existing binary number, or to merge the bits of two binary numbers together. Then we also have the XOR operator, the exclusive OR. This one is like the OR operator, however it results in a 1 if either the top or the bottom digit are a 1, but not both. Almost the same, but slightly different. There's also a NOT operation. This one's really simple, it just flips all digits of a number to their opposite. Zeros become 1 and 1s become zeros. There are also NAND, NOR, and XNOR, but these are just inverted versions of the previous operations. A NAND operation, for example, is just an inverted AND operation. Finally, we can perform bitwise shifting. A bitwise shift can be performed to the left or the right by some amount. Bits that go outside of our maximum number of digits will be cut off, and bits that shift in from the outside are usually set to 0. Next, we'll talk about negative numbers. The easiest way to represent a negative binary number is to pick one of our digits, for example the leftmost one, and make it represent the negative sign. If this digit is a 0, our number is positive. If the digit is a 1, the number is negative. The problem is, if we take these numbers and try to perform arithmetic, it doesn't work. We basically add the magnitude of our number and then add the sign bit, which makes no sense. Also, we can have a negative 0, which makes no sense either. To make the arithmetic work, we have multiple solutions. The first one is called 1's complement. We start by thinking of our sign bit as a negative version of its place minus 1. So here we have the 128th place, and it becomes the negative 127th place. We now take a positive number like 2. Then we flip all of its bits. This is basically the NOT operation we've talked about earlier. The result is negative 2 in 1's complement. If you'd like, you can convert this to decimal and check. Just remember that the 128th place is now actually the negative 127th place. However, there's still something we need to account for when doing arithmetic. Here we are adding two negative numbers together. Notice that we get an extra carry at the end past our negative 127th place. Normally we just cut it off, however in 1's complement we need to add this carry back into our result. If we don't do this step, our result will be off by 1. Looking at a number line of all possible values in 1's complement, we see that there's still a negative 0. This negative 0 is taking up a spot. When we get an extra carry in 1's complement addition, this negative 0 offsets our result by 1. Adding the carry back into our result, however, corrects this offset. Now wouldn't it be nice if we didn't have to deal with this in the first place? Well, that's where 2's complement comes in. It doesn't have any of the problems that 1's complement does. Once again, we change the meaning of our sign bit. This time, we just think of it as the negative version of its place. So here, the 128th place becomes the negative 128th place. Now to convert a binary number into 2's complement, once again, we flip all of its bits. But then we add 1 to it. That's the only difference. This extra step of adding 1 to our negative numbers does something great. It gets rid of -0. Looking at our number line, you can see that -0 is taking up a spot. However, because we added 1 to all negative numbers, everything moved up 1 spot, making -0 and +0 occupy the same spot. Effectively, -0 is now gone. And that means all of our arithmetic and everything else will just work out magically. No extra steps needed. Another way to represent negative numbers is biased representation. We define an arbitrary bias, which is just a number we use to offset our number line. Let's take a bias of 8, for example. The top numbers are what we're actually storing in binary. The bottom numbers are what we want them to represent. So when we want to represent a -2, we actually represent a 6. This works great as long as we remember what our bias is. And this representation is great for comparing two binary numbers, as we're really just working with two positive numbers. Now it's important to note that the bias is added to the bottom number, not the other way around, so drawing the arrows like this might make it more intuitive. Now let's talk about real numbers, like 0.5 for example. To represent a number like that, we need to add a point to our number. Let's just make it easy and place it right into the middle. The places on the left of the point are our good old powers of 2. The places on the right are fractions of 1 over the powers of 2. So the halves place, quarters place, eighths place, and so on. For the rest of this video, I'll refer to the left side as the non-fractional part and the right side as the fractional part, just so we're on the same page. Let's convert a binary number using this representation. As always, we're just multiplying each place with its numeral. Adding them up gives us a decimal number, and that's it. This representation is called fixed point, because the point is fixed in place. Now let's convert a decimal number to fixed point. The non-fractional part is just a regular binary conversion, which we already covered earlier. But how do we convert the fractional part? First, take it and multiply it by 2. Then take the fractional part of the result and multiply it by 2. Repeat this process until we either reach 0 or until we are stuck in a repeating pattern. In our case, a repeating pattern occurs at 0.4. Now that we're done, our bits are actually the non-fractional parts right here from the top down. The non-repeating bits can be written into our number first. And then we take the repeating pattern and repeat it for all the remaining bits. Now if you'd convert this number back, you wouldn't actually get 149.7 that we started with. Why is that? Well, we have a limited number of bits, but an infinitely repeating pattern to fill these bits with. Therefore, we simply can't represent 149.7 exactly. It's only an approximation. This brings us to another problem. If we place our fixed point far to the left, our number has a low range but a high precision. And if we place our point far to the right, we have a higher range but low precision. So no matter what we do, there's always a trade-off. Wouldn't it be nice if you could just dynamically move the point around? Well, that's where floating point representation comes in. The floating point representation is defined by a standard called IEEE 754. In other words, some people got together and invented this standard for how we represent these kinds of numbers. The magic component for this representation lies in scientific notation. You know how we can write very large or small numbers as expressions? We could write 0.000005 or whatever, or we could just write 5 times 10 to the power of -9. This just means we're taking 5 and moving its decimal point 9 places to the left. Well, the same thing works in binary. We can take any binary number and shift its decimal point by multiplying 2 raised to some power. Here we take 110010 and move its point 4 places to the left. The original number we're multiplying is called the mantissa. And of course, up here we have the exponent. We are going to take these and store them in a binary number. Here we have a 32-bit floating point number according to IEEE 754. This is also called single precision floating point. The first bit is a sign bit. The next 8 bits store the exponent. They use a bias of 127 to allow for negative exponents. Finally, the remaining 23 bits store our mantissa. For this example, let's convert 187.7 into binary. First, we take the non-fractional part and convert it like always. Then we take the fractional part and convert it just like we did in the fixed point example. Once again, we end up with a repeating pattern. Let's arrange all bits so far side by side. Before we continue, we do a little trick. The 1 on the very left here is always going to be a 1, so we'll get rid of it. Don't worry, we can do this, as long as we remember to put it back later when we're converting back. This gives us an additional bit of precision. Now let's continue by filling all remaining bits of the mantissa with our repeating pattern. And that's it. I'm going to mark our fractional bits in red, as we need to remember where they begin in just a moment. Next, we find the exponent. Counting from here, how many places do we need to move the point to get it to the fractional bits? That's 7 places to the right, so our exponent is 7. But remember, we need to add the bias of 127 to it, which makes it 134. We convert 134 to binary, and those are the exponent bits. And finally, our sign bit stays 0 as this number is positive. And there you go. That's 187.7 in IEEE 754 32-bit floating point, but not quite. Remember, we have a repeating pattern and our precision is still somewhat limited. So here's what we have actually stored. It's pretty close, but not quite it. For even higher precision, we could use another representation from the IEEE 754 standard. For example, there's the 64-bit double precision or the 128-bit quadruple precision. All these do is they use more bits for the exponent in mantissa, allowing for even higher precision. We can also perform arithmetic with our floating point values. Here are 2 32-bit floating point numbers. First, let's convert our exponent bits. Then we subtract the bias from them to get the actual exponents. Next, remember that we previously got rid of a trailing 1 at the beginning of our mantissa, so we need to put that back now. Cleaning this up a little bit and rearranging gives us these 2 expressions. To perform arithmetic with them, we can either fully convert these back into fixed point, or we can make sure that both expressions have the same exponent. Let's just shift the point of the bottom mantissa to make the exponents both 7. Now we can simply add them together or perform any other type of operation. Last but not least, there are some special values in IEEE 754 that are worth mentioning. A number with all zeros is reserved to be 0. And of course, we can have a negative 0 if the sign bit is set to 1. However, if all bits in the exponent are set to 1, followed by all zeros, the number represents infinity. This can also be positive or negative. And finally, if we have all exponents bits set to 1, followed by any bits other than all zeros, we have nan. This stands for not a number, and it's used as a special result for some invalid operations. And okay, I think that about wraps up the basics. Hopefully you learned a thing or two, and thank you for watching.